Hey there, I'm srcmake, and in this video we're going to go over the solution for IBM's Ponder This challenge for July 2018. So in the video we're going to restate the problem to see exactly what it's asking us, then we're going to go over the logic that we're going to use to solve the problem. We're going to talk about the data structure that we use to actually solve the problem, and we're going to look at some pictures to see how it works out. Then we're going to talk about some of the limitations with that data structure and how we can actually optimize it to get a bonus star. We're going to go over the code, and I'm going to run the code on my computer so that you can see how it runs and just make sure that it works. And then we're going to go over the final answer to see what happens when we run the code. So all of these resources are going to be right here on my website. If you'd like to view this yourself and read it without just watching the video, maybe you want to try the code yourself, click the link below this video and you will get to this webpage and you can follow along. And while you're down there, hit the subscribe button for this YouTube channel. Thanks. So IBM's Ponder This challenge for July 2018. Basically, the problem, which I'm not going to read over, you can pause the video and read it yourself if you would like to, but we're going to think about some triplet of numbers A, B, and C. And this triplet has a particular sum, A plus B plus C, and a product, A times B times C. Now, a triplet is obscure if there is another triplet that has the exact same sum and product as that triplet. So, for example, the triplet 289 has a sum of 19 and it has a product of 144. And the triplet 3412 has a sum of 19 and a product of 144 as well. So these triplets are considered obscure because you can't tell one triplet from the other based on their numbers, or rather based on their sums and products, since they're the same thing. Now, we want to find some A, B, and C where the triplet A, B, and C is obscure. The next consecutive year in this challenge, which is A plus 1, B plus 1, C plus 1 is obscure. A plus 2, B plus 2, C plus 2 is obscure. And A plus 3, B plus 3, and C plus 3 is also obscure. So that will get us a solution to this month's problem. Now, if you want a bonus star, you can find A plus 4, etc., and A plus 5, etc., where 6 total consecutive years is obscure. And we should note that A, B, and C must be natural numbers, which means that they're integers that are bigger than 0. So like 1, 2, 3, 4, etc. Now, how do we actually solve this problem? As far as I can tell, there's no cute mathematical trick to actually make this problem really easy. So the way to solve this is going to be by programming a solution. So our code logic is actually going to be really simple. It's going to be something like this. We're going to check every possible triplet A, B, and C, whatever possible triplets there are. And for each one of those triplets, we are going to store that triplet's sum and product values. So that's step 1 for our solution. And then we're going to check each triplet A, B, and C again. But this time, instead of storing their sums and products, we're going to check if this sum and product value is unique or if it's obscure. So, of course, it'll be obscure if there's another triplet that has the same sum and product as the triplet that we're looking at. And if this triplet is obscure that we're currently looking at this part of the program, then we'll check A plus 1, B plus 1, C plus 1. And if that triplet is obscure, then we'll check A plus 2, B plus 2, and C plus 2 to see if that's obscure. And if that triplet is obscure, we'll check A plus 3, B plus 3, C plus 3. And if that's obscure, then we have an answer. It's a little bit of a lengthy thing to say out loud, but it's actually really simple. And of course, for the bonus star, you'll go up to A plus 5. So we talked about storing each triplet's sum and product values, but what data structure are we actually going to use to do that? Well, actually, we can use a simple 2D table or an array or a grid, spreadsheet, whatever you want to call it. And it's basically going to be like this. So we're going to have this 2D table, and it's going to have obviously some rows and columns. Now the rows are going to represent the possible sums for a triplet, and the columns are going to represent the products for a triplet. And we're going to initialize everything to 0, and basically each cell is going to represent how many triplets have this particular sum and product. And we'll go through an example, don't worry about it. So let's actually just go through the example right now to make this simple. So let's say that we have a triplet 0, 8, and 12. Now, the sum for that triplet is going to be 20, and the product for that triplet is going to be 0. So in our table, what we would do is we would say, okay, at row 20 and at column 0, we're going to increment whatever's there by 1 because we found another triplet with this particular sum and product. So we update this from 0 to 1, and that's how this works. So we'll keep updating the table. So let's say we check 2, 8, 9 as a triplet next. Then the sum is 19 and the product is 144. So we go over to row 19 and column 144, and we update the cell from 0 to 1 because we found another triplet with this particular sum and product. And then let's say we check another triplet 3, 4, 12, and we find that the sum is 19 and the product is 144. Then of course we go to row 19 and column 144, and we increment the value of the cell by 1. So it was 1 before, and now it's 2. Now what this does for us is it says, okay, if a cell's value is 1, then that means the triplet is not obscure because there's no other triplet that has this sum and product. But if a cell's value is above 1, which could be 2, which could be 20, which could be 100, it doesn't really matter. If it's above 1, then we know, okay, there are other triplets with this particular sum and product value. And just like that, instantly we know whether a triplet is obscure or not using this kind of data structure. And of course, inserting these values is also very simple. So we can see that this takes order 1 time for inserting a value because we know the exact place in memory. And of course, this also takes order 1 time to look it up because all we have to do is look up, oh, the sum is 19 and the product is 144. It's this particular spot in the table. So that's the data structure that we're going to use, and that's great and all, but there are some limitations and some optimizations that we can make because of this. So the problem with this is memory, actually. It's not time. Time is obviously amazing. Order 1 can't get better than that. But the memory is going to kill us, and this is why. So let's say that the triplets that we're checking starts from 1 and they go up to a number named n. So maybe if n is 100, we'll check 1, 2 up to 100. 1, 3, 100, etc. Maybe our last set of triplets that we'll check are what? 98, 99, 100, like that. So that's what n is going to be for us. And that means that our maximum sum is going to be n plus n, which is 3n. And our maximum product is going to be n times n, which is n cubed. So in total, we need 3n rows and n cubed columns. And in total, for our whole table, that means we need n to the 4th space, which is a lot of space. So as our n gets larger, as we want to check more and more triplets, our time's still good, but our space is going to explode because it's n to the 4th. That's not, n squared is bad in computer programming. N to the 4th is like way worse. So large n's are going to be tricky for us. So what can we do about this? Well, one optimization that we can notice is that some cells in our 2D array may be unused. So for example, if we look at this particular table, there are so many zeros in here that we initialized, but we're never going to use them because no triplets actually have the sum and product values for those. So we can change the data structure a little bit instead of just using a 2D array or a table or something like that. And the data structure that we can use is either a hash map or a red-black tree. Now, these are actually like really easy to implement, especially in C++. You'll notice that only 3 lines of our code change depending if we change this. And the reason this helps us out is because, let's say we use a red-black tree, a cell will only actually get created for us if we have that particular sum and product for a triplet. So if, let's say, a particular sum and product, let's say we have a sum and product in the table, we'll have to initialize it to 0 no matter what, even if it doesn't exist. But in the red-black tree or the hash map way, then this will only get like initialized if this product and sum exist. And that's a little weird to explain. I don't want to go over the data structures. I have another tutorial on data structures that maybe I'll have a link to a data structure tutorial below this video if you want to go through that, but that's how this works. So let's go through the code. I'm going to go through it with you right here, and we're going to see what's going on, and then I'm going to run it really quickly. So we first initialize, and this is C++, by the way. It's not a big deal. You could probably use any programming language, but I like C++. So we initialize our n to 100, which is going to be the maximum number that we check for our triplets. And this is going to be the array way. We just initialize a table with everything set to 0. And the red-black tree way is going to be just a map in C++ where we have a pair that represents the sum and the product, and that maps to a particular number of values, the number of triplets that have that sum and product, as we mentioned before. Now we have another function right here, is obscure, and it just checks the table to see if a particular triplet A, B, and C is obscure or not. And this is the array way, this is the red black tree way. Really simple. Another just one line of code, different change if you want to use the red black tree. And next we have another function named add to table. So this just adds a sum and product to the table. So let's say we have a triplet with a particular sum and product. We want to update our table to let them know we have another triplet with the sum and product. You just do this line of code or this line of code, array way, red black tree way. And I just want to point that out because it's like such an easy, quick data structure change. So that's it for the data structure stuff. Now we'll see what we actually do in the program itself. So we check each possible triplet. We start A at 1 and we go up to n. B goes from A plus 1 up to n. C goes to B plus 1 up to n. Just check our triplets that way. And of course, we don't want to have like the same triplets over and over. So that's why we have B equals A plus 1. We don't want to do like 1, 1, 1 because first of all, that's not a good way to do things. And we don't want repeats. That's inefficient. So for each triplet that we check, we'll get their sum product, and we use the add to table function to do that, to add it to the table. And now once we have that table filled up, then what we want to do is go back through the triplets one more time and just check if they're obscure. So same exact for loops to go through the triplets. And this time we use an if statement to check, is this triplet obscure? If it's true that it's obscure, then check the next year, which is A plus 1, B plus 1, C plus 1. If that's obscure, then check the next year, etc. And finally, if we get to a value that we like 4 consecutive years of obscure, then we just output the answer using cout. And of course, we can keep going for A plus 5, A plus 4, A plus 6, etc. as far as we want to go. Now, this looks a little messy, and I'm sorry about that, but that's actually I found it to be the best presentation way. There's a lot nicer, neater ways to do this using functions, but this is easier to present. So I'm going to copy this code, and you can see that I've got this file named main.cpp. I'm going to paste the code right in here. Now I'm going to open a terminal. I'm going to type bash, and that's going to make this a Linux terminal. Then what is the actual lines? I forgot what it was. Usually I just use make files because my name is srcmake. Make files. So G++ to compile it. And you can see that the compilation takes a second, and then we do /run to actually run the compiled executable. And did I press enter? I think I pressed enter. And just a second goes by, and you can see that we have some answers. So let's go through the answers right here. Oh, I shouldn't have closed that. Whatever. So if you run the above code using the array way, then you'll get a bunch of answers in a second, and it's really simple. And you take any one of these, you email it to ponder.il or ponder@il.ibm.com. You get your name on this pretty list. But let's say you want that bonus star because, bonus stars are kind of cool. Everyone likes that. What would you do? Well, you go back to the code, and what you want to do is, let me open this up just to show you. What you'll do is you'll change n to 1200. Now, if you try to do this and you try to compile it again, you'll get an error. I think you'll get it here because, you're trying to compile too much space for this array, and that's you can't do that much space in an array in C++. So what you want to do is you want to switch from the array way to the red black tree way. And there's a line of code right here that's going to explain how to do this. So you just comment out the array stuff, and you uncomment the red black way stuff. And that's just 3 simple lines that you do. Now I'm going to change it to 100 just to show the red black tree way. And you do that, and oh, it didn't output anything. Why didn't it output anything? That's super weird. I don't know. Oh, because I didn't run the executable. That was dumb. I was why? Okay, so you do that and you get the exact same answers using the red black tree way. If you want to get the bonus star, then you set n to 1200, and boom. It takes a really long time, and actually, let's go over the numbers really quickly. It took me 10 minutes using n up to 1200. It took my computer 10 minutes to fill the tree. with the table. And it took 17 minutes to check all the triplets for obscurity. So basically half an hour of this program running if you want the bonus star. And it took 12.5 gigabytes RAM on average, and it peaked at like 13.1 gigabytes. So it does have some memory limitations, and of course, using the red-black tree, it took some time too. Maybe the hash map would have been quicker, but the code was a little bit messier, so I didn't want to present that in this video. So it's that simple for the IBM challenge this month. I honestly think it was a really simple programming challenge, and you can see that because like so many people have their names on, and it's only like July 9th right now, so that's pretty crazy. So if you did solve this, great job. If you wanted the bonus star, this was the way to get it. And I can't think of a better way to solve this problem. So if you can think of a better way to solve this problem, then go ahead and leave a comment below this video. Make sure you like and hit the subscribe button if you want to see more of these solution videos to IBM's Ponder This challenges each month. And I'm srcmake. That's been the challenge. Thanks for watching.